constraint. Here's our constraint equations, and we see that they are a function of force and instant center locations. On the right here, this schematic is just showing where these constraints are acting, and once again, they're acting as the instant center. So just like to emphasize that these are the constraint forces found as an equivalent set of friction forces acting at these instant centers. So this is our power model. We're going to just use torque and angular velocity to find instantaneous power at each track. We're going to sum that, and then we're going to integrate over the entire path to get the energy consumed. And this is possible because we solved our equations of motion and have our constraint forces we can solve for torque. So here we're going to suggest an iterative solution for solving our dynamic model. First, we can specify trajectory inputs of the chassis, velocity and acceleration. And then we also need our current global location. We'll then provide an initial guess of our slip kinematic parameters. We can use those to solve for the constraint forces from the friction model. And then we use that to solve for the equations of motion, get the new set of slip kinematic parameters. And then we'll iteratively repeat these last two steps until we find a set that is no longer changing at some tolerance. We can use that set to solve for power and energy, and then we repeat the whole process for the next time step. So since the dynamic model is the fundamental principle of our work, we're going to show a quick validation. So here is our experimental setup. We have a climbing skid steer robot operating on a vertical steel surface, and it's going to be commanded to operate or to maneuver in a nominally circular path. On the right here, these are our results. So I'll start with the black path. The black path is what the robot actually maneuvers. So we see that there's a high degree of slip compared to a nominally circular path. The red path is showing an assumption of constant slip kinematic parameters. So if we say that these slip instant centers are not moving, well, with a high degree of slip, we're not going to predict our motion very well. And then with the blue path, this is what we do. We're assuming our dynamic set of slip kinematic parameters, and we see that we get a much better estimation of position. So this is just taking a closer look at these instant centers. On the left is a few example paths. Again, it's a nominally circular path, and we see that we have 5 different payloads here, and as the payloads increase, our path becomes more of a spiral down the wall. And on the right, we see corresponding instant centers. It happens that the instant centers create a closed loop locus for the circular path, and as the instant centers get farther away from the robot, we have a decrease in efficiency. So here's taking a look at the effect of this slipping with regards to power. So we know that this slipping creates asymmetrical instant center locations with varying magnitudes. So here we command a simulated robot in a simple curved path on a vertical surface, and this is shown in the XY global frame. On the right here, we have energy consumption with respect to the X displacement. Here we are comparing the kinematic assumption of slip kinematic parameters, and this is our dynamic slip kinematic parameters. So we see that the kinematic assumption gives us a conservative estimate of energy consumption. So we're going to look at 2 applications. or two ways that we can do this. We can reduce the total turning required, but we can also find a path that positions the instant centers in a way that reduces the instantaneous force required. Any questions?
You optimized your path by just looking at 2 points in the middle?
Yes,
Correct?
2 waypoints.
Did you look at 3 or 4 to see if that would help to decrease it?
We could do that. We didn't in our case, just to show the principle. But this is an ongoing research, and we will be doing things like that.
Thank you.
One question I had was, you had 2 waypoints in your final graph. So why isn't your robot just going straight from one point to another, it's rotating, going from that point to the final point, for example? Why is it going on a curved surface? Curved trajectory?
Oh, in this case, okay. So this is mostly, this is a linear segment here, but we have a velocity